Hello, today we will talk about hashing technique. So this is our class objective. So we would like to understand the basic hashing technique based on these hyperplanes, also hypersphere. This technique actually is one of very common unsupervised technique that does not require any labels. And then also we will briefly touch on one of the supervised techniques for data set that comes with the labels. And the last time we talked about the re-ranking method based on the spatial verification, also this query expansion. Also, we talked about the inverted index that can accelerating our search performance. So up to last time, we actually talked about these different components of some of the recent this image search system. So given a query. Given the query, we first identify some of the nearby clusters, right? And then we know, what are the actually associated images for each cluster by using the inverted file or the inverted index, right? And then we instead of exhaustively testing all the images in the DB, we can only look at these images associated with those cluster, right? So that basically we actually reduce down the search space a lot, so that we can improve the search space. And then out of those images, we perform the more fine level, actually the matching or computing the similarity between images. We can at that cases we can look at the image descriptors, so image features coming from the SIFT or the GIST or the CNN features, and then we compute the short list, and then we can also run the re-ranking and then compute the final result. They can be returned to the user. These are actually some of the main structure of the recent image search system. Again, now let's look at the image search operation. So basically, the image search is nothing but finding visually similar or the semantically similar image, right? But the definition of visually similar or the semantically similar depends on your applications. Basically, we need to have some sort of the similarity function or distance function that give us that give us the meaning of that information. But at high level, we need to actually we are using some sort of the image descriptor, right? You can use the Vega visual word, GIST or color histogram or the recent CNN features, right? And then image is nothing but we treated you can think that the image is nothing but a point in a very high dimension space where that high dimension space nothing but basically there is the space of our image descriptor space, right? So if you're using the CNN feature, that CNN feature might be in this 4,000 dimension, right? Then basically this image is nothing but just a point in that high dimension space. And then if basically these images nothing but mapping to some point in here, right? And then basically over there we can define some sort of actual distance function, right? So basically the meaning is that as we for these two images actually somehow mapping to these 2 points that are actually located very closely, and then you can see that their distance is quite low, right? And then it means that as we have the lower distance, it means that we can treat that these two images have a similar feature or semantically similar content, right? So basically, we can just using some sort of the L2 distance or some other distance function within that feature space, right? But higher level, we wanted to build the feature space that such that way if these two similar images, visually similar or semantically similar image should give us the very small distance in that space, right? So basically, it boils down the computing feature space. Along that line, we can use the CNN one, right? So bottom line is that then image search is nothing but given a query image, we wanted to identify this most similar, most closest neighbor within in this high dimension space. In other words, image search nothing but performing nearest neighbor search in this high dimensional space. So basically the nearest neighbor search (NNS) is one of the very common common operations used in their some database related to some sort of the proximity computing. So now let's look at the issue. So here in this high dimension space, we might also have a lot of images, right? And then as I mentioned before, if you are using the CNN feature, the CNN feature has each point has a 4,000 dimension, right? And then think about it. If you are using the backward visual world, you can treat that each dimension, dimension of this descriptor backward visual world can have the more than 1,000 dimension, right? And then you can think that we can use the 4-byte integer for each dimension, right? And then one image actually has the 4 kilobyte size of this backward visual world descriptor, right? And if we had 1 billion images, then it means that storing this image descriptor require 4 terabytes, which is a lot, right? Same thing for the CNN. CNN has more than 4,000 dimension, and then if you're having the 1 billion images, then it means 16 terabytes actually, which is a lot. So in my lab, some of this server has the 144 gigabyte, right? So if we wanted to, if we want to have the very fast search performance, we should have those descriptor on the memory, right? And then if we wanted to put all those if we want to put this 1 billion image within that 144 gigabyte of the RAM, it means that we can only use the 128 bits, not even byte, 128 bits for each image, right? So it means that we cannot use a lot of the space for recording this kind of image descriptors. So basically, if you go back to the overall system, here I mentioned that at some point, right? Here actually the inferencing file, we can just using the sum of index of your image descriptor, right? Here actually it might contain just a 4-byte index, right? 4-byte integer, right? And then here when you compute the shortlist, then we need to, I mentioned that we need to do some sort of the more fine level matching, right? At that case, we need to look at the descriptor, and at least we need to perform the L2 distance in terms of the matching, right? Using the L2 distance with the descriptor, right? Even at that case, we need to use this descriptor, right? So then it means that we need to store this 1 billion these images of the descriptor in the main memory. Otherwise, it might we need to basically we have to access the disk, which is very slow operations when we are doing the search operation. So this is actually one of the biggest big challenge for the efficient image search in terms of the web scale size. So basically, one can think that actually if we can actually somehow encode this image descriptor with the binary code, then it will be very useful, right, in terms of this compressing this memory requirement, right? So actually, I'm not the first one who think about this issue. Actually, there are researchers who are think about this one. So somehow, given this CNN feature or some other features, we wanted to have actually very compact binary code for each image, in a way that similar image has a similar binary code, right? In this case, we only have this 5-bit length code, right? And then also different image has a different bit code, right? And then if we can do that, then actually we can run this image search within this space. But actually each image descriptor, in this case, is a very compact binary code. Then it will be we can actually store all of these binary code in the main memory, right? And then we can do the image search in a very fast way. That's actually one of the benefit of using binary code. So as I mentioned earlier, the data using binary code actually comes with a lot of benefit. We can compress a lot. Also, it actually turns out that it is very fast distance. I mean, we can do we can compute the distance between these two descriptors in a very fast way. Since the recent CPU and GPU actually can provide a very fast distance computations. I will talk about the Hamming distance, right? Hamming distance is nothing but just number of bits that has the different bit value. In this case, their Hamming distance is 0, since they actually have the same bit code, right? But here we only had only one Hamming distance, since actually there are only one bit difference, right? And this Hamming distance can be computed by some of the built-in intrinsic this bit operation, XOR operation, something like that, which is actually the recent hardware actually extremely optimized. So these are actually the benefit of using binary code. So recent technology using this, they use this binary code instead of the original image descriptors. So again, we basically we use the image descriptor instead of the raw RGB data, and then we also even compress the image descriptor with this kind of binary code. Along this line, most of the prior technique used this hyperplane based binary code. So basically, here actually I'm just even though this image features in the very high dimension space, I'm just showing the 2D illustration. So in this case, I just using the plane over the line. So obviously, this line or plane actually extended to the hyperplane at that kind of high dimension space. And then here we have the bit. We have this kind of the point. Actually, you can treat that each the point nothing but just encoding this one image descriptors, right? And then we just using this hyperplane. This line, and then we treat that all the points located left side of this line actually has the 0 bit, right? And then all the other one has actually the 1 bit code. This value of 1. Then basically if you at one time if your core image has located there, and then the core image assigned has this bit value of the 1, right? And then we can treat that older image descriptor that has the same bit value, in this case 1, can be treated as actually same kind of the candidate for the very similar image to that core image, right? So obviously in this case, since we only used only one bit bit code, bit length, actually a lot of the very diverse set of image actually has the same bit code, right? Then obviously to differentiate more, we can use the more bit code, right? In this case, we used actually 3-bit code length. So along this line, for the left one 0 bit 0 bit value, the right one value, right? And then also used around the hyperplane. Depending on this one, we actually assign the 0 and 1, right? And then for image actually located there, it has a 0, 1, 1. For image actually located there, you can actually have a 1, 1, 0, something like that. Then we can actually we can narrow down the search. In other words, if the core is located there, we can actually treat that the images actually containing the same bit value actually are the candidate for the similar images, something like that. Then it means that we can only access those images for matching. Instead, then we don't need to look at all the other images. Then, as I mentioned before, we can do for measuring the distance between two binary code, we can use the actual Hamming distance, right? And then, so basically, for this image, for that image, it's the Hamming distance has only the one bit length, right? Only one. But for this image, that image, actually, the Hamming distance actually three, since the bit value is actually different. Any question up to here? Do you have a question?
Yes, but I don't know how to find the hyperline.
Yeah, then I will get back to that issue. Yeah, now. Yeah. So the question is how can you construct this hyperplane, right?
Yeah.
That's a very good one. So here, this is actually the slide. So here I have the two examples. Given the same data set, we can construct hyperplane in this way or that way, right? Which one looks more promising, good to you?
One.
First one. Can you explain why?
It's balanced.
Huh?
Balanced.
Yeah, well balanced, right?
Yes.
That's correct. That's the main reason, right? So basically, you can see that if we actually have this kind of the partitioning, right? Then this region is very small, but this region is very wide, right? Then it means that a lot of the different set of the image actually has the same bit code, which is bad for the searching, right? Same thing. So I will actually talk about that one. But my main point is that a lot of technique also they actually a lot of technique actually designed to design based on these hyperplanes. But actually we are here from now on. I'd like to talk about the spherical hashing, which is based on this hypersphere. But actually a lot of actually it has a different representation power. But also a lot of technique also they're based on the prior hyperplanes. I will talk about I will talk about how we can build this kind of hyperplanes or hypersphere later on. First of all, I'd like to actually talk about this concept of the spherical hashing. So far, I talked about I used the hyperplanes to partition the data, right? But why not using hypersphere, right? In this case, we're just using the circle in the 2D case, right? And then the data, all the points that are located within this circle has their bit value of 1. For all the other ones, we assigned 0, right? This is a concept of the just hypersphere. A little bit very similar to the hyperplane, but instead of the hyperplane, we're using the circle, the concept of the sphere, right? And then for the 3-bit cases, we can just using we can use three circle. And then for each circle, we can define 0 and 1, right? Something like that. So this data located within all of 3 circles has the 1, 1, 1, something like that. And then this data outside of all the circles has the bit value of 0, 0, 0, something like that. That's the example of the hypersphere. Now I will talk about why we need to use the hypersphere. This one, right? So here I'm showing the different example of using 3 hypersphere or the 3 hyperplanes, right? So it's by now it's already unclear to think about it which one is actually better, right? But actually it turns out that basically here let's see that in the case of the hyperplanes in this region this kind of closed, right? But if you look at the other regions, right, and then these regions actually kind of open. It means that some part of the region actually bounded by hypersphere, but some other regions actually unbounded, right? It means that since it's open, there could be a lot of the data that are located very far away, right? Even though they are located very far away, they are actually having the same bit value, right? Which is actually bad, right? Even though the same bit value, some of the data actually located there, some other data located there, which is very far away from the prior one, right? Which is bad. But if you look at the hypersphere case, then a lot of the regions actually kind of bounded, closed, right? It means that if we measure their distance actually those two values, those two data is located having the same bit value, but their distance kind of bounded, right? Which is good for the actually searching. Also, they're representing actually the similar nearby data with the same bit value, right? So if we actually measure the average of the maximum distance, they're having the same bit value here, then actually the average distance of using the hyperplanes actually having this average distance of something like this actually. As a function of the actually wider, bigger, more code length. So as you can see, as we use the more bit length, actually their distance going down. But if you're using hypersphere, their actually average of maximum distance is actually much lower than that one, right? It means that we can by using hypersphere, we only assign the data which are much more closer compared to the prior approach with the actual same bit value. So that's the main benefit. And then the main reason is that actually by using hypersphere, we can define the more close region, while by using the hyper plane, there could be many of this open space.
So hyperplane is just for we just want to divide the images into several
several regions for assigning the bit value.
But I think if some image is very close with another image, but we just have a line.
Right. That's a quantization effect. That's also quantization effect.
Yes.
also there actually there's another paper they're mainly looking at that issue. We are not going to talk about that issue, but that's the kind of general issue of the doing the any partitioning or any clustering or any quantization. Okay, so in terms of actually defining closed region, think about actually there. Suppose that we have actually 1,000 dimension. To define a single closed region, how many hyperplanes do we need to have in this based on the hyperplane setting? 1,000 dimensions to define the one closed region. How many bits? How many hyperplanes do we need to have to define a single closed region?
1,000 dimension.
Yeah.
What's the way to know?
Huh? So think about it. In a 2D dimension, how many lines do you need to have to define a closed region?
4,
3.
3.
1, 2, 3, right?
Right.
In other words, n dimension space, we need to have n plus 1 hyperplanes. But how about the circle?
Yeah.
To define a closed region, how many hyperspheres do we need to have? Surprisingly, 1. So it means that it actually hypersphere has a fundamentally different actually the characteristics compared to the hyperplanes. And then since actually the obviously the closed region is much better than the open space in terms of the bounding the data that have the same bit value. So as a result, actually using hypersphere actually they're much better than the the plane. So obviously here actually also one can think about actually we can even use some other representation. You can even think that we can use the recent deep learning to compute this kind of the binary assignment actually, which I will talk about later on. And then how can you actually how can you compute this hypersphere? Basically, in the case of the hyperplanes, these are actually the very well-known criteria. Obviously, we need to have the balanced partitioning, right? And then obviously, for 2 cases, here 2 different hyperplanes, which one might be the better than the other one? Second one, obviously, right?
Yeah.
This actually they're redundant each other. And then even though we are using the secondary one, it doesn't give any information, right? So it means actually when you have the new hyperplane, it should be independent from the other one. So we can apply the same approach even for the hypersphere. So when you actually assigning one hypersphere, the data within the hypersphere would be the half. Also, data outside of hypersphere would be also the half, right? Which actually indicating to the balanceness. And then also we can also assign the independent. When you are using the 2 hypersphere, basically each region we should have the 1/4 the data, right? Basically based on I didn't talk about the mathematical derivation, but if we actually think about it, independent property of the independent property, then based on that actually we can have this kind of data distribution out of the 2 events. Event here actually nothing but whether the data is located inside or outside of the hypersphere. Basically, knowing this exact, I'm just giving high level intuition instead of the actual very low level definition derivation. And then how can you compute the hypersphere actually? Which in terms of actually hypersphere, we need to once we set the center, then we need to adjust the radius, right? But we just adjust the radius in a way that the data within this hypersphere has to contain half of the data for the balanceness. And then for the independent property, actually once we had this 2 hypersphere, we need to look at how many data actually in each region, and then we actually push a pull of those 2 hypersphere in a way that the data distribution follow this independent property between these 2 spheres actually. We keep doing that until we converge. Now let's talk about actually the distance function. Basically, distance function nothing but the similarity function. But here we can just using the Hamming distance, right? But if we visualize the maximum distance, they're having the same of the bit value of 1. In this case, these two data actually has their one same bit value of 1 here, and this turn out to maximum 1, which is a lot long. But actually, if you are looking at the data, they're having the same 1 bit value. In terms of the two bits actually having the same 1 bit value, then these two data actually they're located the maximum one. They're having their basically the two bits actually having the same bit value of 1, something like that. Then actually, if we computing that one, as we increasing number of the common of the 1 bit value, actually their average maximum distance actually reducing down as a rational function, right? Then we wanted to encode this property within this spherical Hamming distance. Spherical Hamming distance nothing but actually this spherical Hamming distance starting from the just regular Hamming distance bit basically the number of the different bit value, but which is divided by the actually common 1 bit value actually. Since we actually had this kind of basically their distance actually dropped as of this rational function.
Really?
Huh?
So you mean the more common one we have, the distance will be larger, will be smaller.
Yes. So basically their distance actually dropping down in this shape.
Yes.
So that's why to consider this fact, we actually have this term, right?
Yes.
So even though same basically it's not a linear, right? So that's why actually we actually have this kind of the factor.
Yes.
To follow that property. Okay, so basically my main point is that we actually we thinking about how we can build the hypersphere, hyperplane, right? That's kind of representation how we construct the bit value, right? That's the kind of our process of computing this representation, kind of feature representation in terms of binary code. Now we are talking about what are their distance between the representation in terms of the binary code, right? You can see that same meta structure keep going on, even after this kind of computing the hashing or the binary code embedding. Also, we do the same thing even the deep learning. It actually indicates that we can actually apply this tech. We can actually extend this technique to the recent deep learning. Actually, we had this one before a long time ago before we actually had a deep learning, but compared to this actually x-axis actually the binary code length, y-axis actually accuracy. I'm not going to talk about the exact definition, but higher one give us the higher value indicating that we actually can identify more similar images. As you can see, by using our spherical hashing, spherical hashing based on the hypersphere, this one using spherical hashing with Hamming distance. Then at that case, actually, as we use the more bit length, we are showing the better accuracy over the prior one. But by using the spherical Hamming distance, just a minor change, then we can get a much better actually accuracy. So I'd like to point out the importance of this distance function.
What is MAP?
MAP is the mean average precision, something like that. I didn't really talk about that one, but actually measure it actually related to the actual accuracy of our search system. I will talk about MAP later on. Probably. Just to think that higher value is better. Actually, we also although by using this binary this hashing technique, hashing also you can treat the hashing also binary code embedding. Then we can actually encode the binary. We encode the CNN feature with this binary code, so that actually we can embed. We can actually store all those binary code with the CPU, so that actually we can run this image search with the 11 million images within the 35 milliseconds with the single CPU thread. So that's the main benefit of using the binary code. So that actually somehow we compress a lot drastically. We are talking a factor of the more than 1,000 or 10,000, something like that. and then so that we can do the search system with the only with the main memory without accessing disk, right? And then if you need to know if you want to know the more higher matching, then you can access the image descriptors, right? Then at that case, you just touch on only basically we just compute the short list, say 1,000 short list. Then you can actually access the original CNN image descriptor. Then you can do the re-ranking based on the original image descriptors. That way you can improve the accuracy. Okay, so far I talked about unsupervised technique, right? So I didn't talk about any of these labels, right? So basically we so far in the case of unsupervised case, actually the similarity governed by the actual distance function or the similarity function, right? But some of the image has a label. Some of the image has a label of cat or dog, right? Then in that case, we need to treat that image that has the same label should be treated as a similar one, right? So for that case, actually, we can talk about supervised hashing, right? And then some of the technique also based on the deep learning. So actually, now I'd like to briefly touch on some of the supervised technique with the deep learning. There could be a lot of technique, but actually I'd like to talk about one of the early approach. So so this technique actually it's not really end-to-end deep learning wide end-to-end training. Actually, this technique has a two-step. First step is that they somehow approximated hash code. So first of all, actually they computed the similarity matrix. It means that actually this similarity matrix. Basically when two images I and j have the same label, we give the 1. Otherwise we give 0, right? That's like similarity matrix between these two set of between all the image pairs, right? And then we wanted to somehow represent the assign binary code for each image, right? So actually that's actually known as Hamming embedding. Hamming embedding is nothing but binary code embedding. And then we actually assign we somehow assign the Hamming binary code for each image, right? And then we wanted to approximate this similarity matrix between dot product between two of these Hamming two of these binary code, right? In a way that their dot product between initial initial hash code binary code give us this S matrix, the similarity matrix, right? And then they didn't use the deep learning. They used some of the approximation techniques. I'm not going to talk about here, but I'd like to point out that this is not based on deep learning. And then at the second step, they mainly focus on the learned image feature. They wanted to learn the image features hash function that gives that computed hash code, right? And then to compute hash code, they use different technique actually, some of the very classical approaches. And then they actually use the AlexNet, just the CNN, some of the CNN, the basic CNN network. And then we actually do the same. This actually very similar CNN approach here. And then we at the end of here we used some of this fully connected layer that give you that try to follow basically here I would say that this Hamming code is the approximate Hamming code, binary code, and then we actually have some sort of classification one that follow our computed approximate target hash code. If this code gives the 1, we want to give the 1. If gives the 0, we want to give the 0, right? That way we want to compute this kind of features, right? That's the main difference between how they compute how they utilize the AlexNet for modifying the AlexNet to their computer binary code. And then also this as optionally they also this image comes with the label, right? And then also they used this computer also they wanted to compute the feature in a way that they can also predict exact these labels. This second another task. Based on these two tasks, we can also define actually the most function here and there, right? Based on that, we compute the feature. So in bottom line, they designed their technique to compute the feature in that way. But as you can see, this first step, second step, they are decoupled, right? It's not a fully end-to-end technique. As you can see, some recent technique, actually they designed they somehow integrate even this first step within the deep learning, so that they can do their actually end-to-end training. That's if you're interested, I recommend you to look at some of the following techniques. Okay, so far I talked about actually basic hashing technique, which is actually based on hyperplane or the hypersphere, which is actually the unsupervised technique where we don't use the labels. But I talk about some of one of the early techniques, actually of the supervised technique using the deep learning in some of the components. Also, there used some of the here code of the using hypersphere actually available at the web, and then you can actually using this one. And then the follow-on assignment, program assignment, we will actually you will actually get the chance to try out this binary code, watch the benefit of the using binary code in terms of actually accelerating accelerating running performance of image search, which will come later. Any question, comments up to here? Okay. So the regular homeworks, go over the next lecture slide. Come up with one question on what we talked about. Just the writing, submitting 3 questions is okay before the midterm exam, and then go over the recent paper and then submit their summary before the Tuesday class. And next time I'll talk about some of the more advanced CNN based image search techniques. Yeah, that's it. Thank you. Bye.